Okay, our next speaker, giving an invited 30-minute talk, is Young-Joon Kim, who's with the National Weather Service. Yes, it's on. Who's with the National Weather Service, and he's a former Arakawa student. And he'll be talking to us about what Professor Arakawa left him, including the Kim-Arakawa scheme.
Can you hear me? Okay. So thank you, Dave. First, I'd like to thank the organizers of the symposium for giving me an opportunity to share my story with Professor Arakawa and some work done with him. My name is Young-Joon Kim, also known as YJ. I'm currently the Chief of Analysis and Nowcast branch of Analyze, Forecast, and Support Office of the National Weather Service headquarters. It's good to see all of you here. For those who are not familiar with National Weather Service organization, this is an org chart which was updated several years ago due to the reorganization. So we have some high-level offices. We have two main offices, what we call the left side and the right side. It's too long to remember. So the left side is to enable missions, and the right side to operate the missions. And under the right side, there is an AFS office that I work. And we have a code like AFS 11 to designate Analysis and Nowcast branch, but it will soon be expanded to Analysis and Forecast branch to cover the whole spectrum. Anyway, we work with what we call NSAP, you know all this, and also the regional offices and a lot of weather forecast offices, river forecast centers, and central weather service units for aviation. And we deal with them to kind of implement their needs. On the left, there is an STI office, and we coordinate kind of in between STI and NSAP to make sure that the models are delivering something useful for the forecasters. And this is how it started. Picture on the right is Professor Jung-Woo Kim, who I met in Yonsei University a long time ago. And he was my professor ever since. And after I graduated from college, I wanted to study abroad. And Professor Kim strongly recommended me to go to UCLA to become a student Professor Arakawa's. So I remember I didn't apply to any other school but UCLA, and I got it. I got the admission pretty fast, thanks to Professor Kim. And I came to UCLA in the next year. And this photo was taken in 1990. I can't believe I'm that old, but when Professor Kim visited UCLA, so it's like 3-generation photo. And this was taken in 1996 when Professor Kim's and my families visited Professor Arakawa's home in Santa Monica. And it was after I got a PhD from him. And I continued on to work with him after I graduated as a postdoc and a researcher later. And from 1996, I started working for the JPL, so it was part-time basis, but I learned a great deal about modeling from him. In the meantime, Professor Kim became a renowned climate modeling expert and lecturer, very famous lecturer in Korea. The left photo is also taken in 1996, showing families of myself, Professor Kim, and Professor Arakawa. On the right is taken in 2018 when I visited his home in Santa Monica, and I had no idea that would be my last moment in this life. So I was fortunate to visit him. So I'd like to talk about how the Kim-Arakawa scheme was born. When I first came to UCLA, he taught me the famous or infamous Arakawa paper, and I had no idea what that's about. But I studied hard for 2 months, and I told him, sorry, I'm not interested in this. I heard Professor Kim did the same thing. And he recommended, okay, how about radiation? So after a few weeks of study, I don't get it either. So he said, okay, then pick your own topic. So after some search, I picked relatively ill-known subject of gravity wave drag, simulation and parameterization of it. And I want to take this opportunity to thank Steve Kruger. I learned a great deal about numerical modeling from him, and he helped me build my mountain wave model. So thank you. This is from a paper and showing streamlines over a barrier. So I came up with some formulation based on this explicit simulation, and the scheme failed miserably because the parameter scheme is supposed to capture something going on over a barrier, and then it didn't feel anything. So I was struggling quite a bit and ended up with narrowing down the domain, which I thought was a cheating effort. But anyway, I was able to find some domains that fail something. I mean, the scheme detects something, and I had to report to Professor Arakawa and brought it to him. And surprisingly, he was very excited about these weird ideas. And he encouraged me to continue on. And eventually, this algorithm evolved into what we call Kim-Arakawa orographic drag parameterization scheme. And versions of this scheme are used worldwide in operational global and regional weather and climate forecast systems. So it's so natural in modeling, but I learned to experiment, fail, learn, and repeat. So that was a lesson I learned. And this is a list of systems that includes some version of this Kim-Arakawa scheme. And of course, started with UCLA GCM. I mean, it was called at the time as UCLA GCM. And I remember visiting Dave Randall to implement my scheme, but I don't think it's still there. I know it's too old, but I tried anyway. But there are a lot of systems used by NCEP that are kind of successful. The global forecast system, climate forecast system, I mean, this is going away and unified into GFS. And something called NAM, North American Mesoscale Forecast System, and something called HER and RAP, High Resolution Rapid Refresh Model, and Rapid Refresh Model, the low resolution counterpart. This is a next generation system called RRFS, Rapid Refresh Forecast System, and the famous WRF. And when I worked for the Navy, I implemented it into the NOGAPS model. And I used to direct an institute called KIAPS, Korea Institute of Atmospheric Prediction Systems, and it's there. And another Korean model, GRIMS, and a Chinese model, but I don't know what happened after a long time ago. But there are more models that probably use some versions of this scheme. This is very simplified schematics describing the scheme. So there is a barrier, waves are launched and break, creating gravity wave drag in upper level layers and also in the downstream. And there is blocking by the barrier, flow blocking. And the original Kim-Arakawa scheme takes care of the breaking part, and it had very crude but practical way of representing the blocking in the 2D sense. But 10 years after the original scheme, I came up with the idea to fully implement the 3D effect with more conforming to the physics. So this is an extension, and introduced something called orographic direction for the full 3D effect. Friends of mine came up with some way of generalizing the height of the block layer, and that's the basics of the scheme. Pretty simple, but the weird part was this, additional orographic statistics. At the time, virtually all the schemes just used standard deviation of orography, which is the first moment. But I thought after kind of many simulations with the model, that probably I can match the geometry of barriers to the characteristics of the flow. So first I thought about how it is tilted. For example, this one tilts more toward the downstream, and that launches stronger waves, more nonlinear waves than the other case. And although you have a very regularly shaped mountain, depending on where you put it in the domain, they correspond to different waves and effective waves. And also, depending on how the slope and sharpness of orography, they respond differently. And all these barriers share the same standard deviation, meaning at that time, other schemes were not able to distinguish between these different characteristics. And I didn't like the assumption of bell-shaped mountain conveniently located in the center of domain. So I came up with a way to measure the bulk volume of orography this way. No time to go into details, but this is very different. And of course, orographic direction. So this weird part turned out to be the key aspect of the scheme. And there are many applications, but I particularly like this subject. I think I'm talking too fast. Anyway, so there's something called sudden stratospheric warming, SSW, which is an event where polar vortex of westerly winds in winter hemisphere very suddenly slows down or even reverses direction. And that is accompanied by a sudden rise of stratospheric temperature. That's why it's called sudden warming. That's known to be caused by breaking of vertically propagating planetary waves and also gravity waves originating from the troposphere. And when that happens, not always, but in many cases, the middle atmospheric disturbances come down to the surface and affect the surface weather greatly. And you can measure it by Arctic oscillation or NAO, North Atlantic oscillation, depending on the area and region. AO is a large-scale seesaw in atmospheric mass between the subtropical high and the polar flow. And one of the most popular, well-known phenomena related to this is polar or Arctic blast. When the vortex slows down, the jet starts meandering, and in some areas, the cold, warmer but still cold Arctic air penetrates into south, and it sweeping the whole continent. And no matter how good your regional models are, if you don't get it right from the global models, you're not going to get the right forecast. So anyway, this is very important mechanism that a model should represent. And I tried to, because the gravity radar is launched, I came up with the idea of testing my scheme, Kim-Arakawa scheme, to improve this. And for the 2009 case, I was able to improve this onset of SSW using a package I came up with, showing improvement over the control version. So bottom line is the Kim-Arakawa parameterization improved the middle atmospheric and tropospheric coupling, and that was key to improve the predictability of the model. So this is a way to improve model performance. And between then and now, there are many things that happened, but I'd like to show just one example, which is taken from an AMS talk by a group of scientists at OAR Global Systems Lab. And they came up with this unified gravity wave physics suite for NCEP global models, global forecast system and global ensemble forecast system. And the package consists of, first of all, the formulation based on Kim-Doyle's parameterization, which is an extension of Kim-Arakawa, for large-scale gravity radar. And for low-level flow blocking, they also follow Kim-Doyle work. And this is very interesting because some European scientists came up with an idea of applying this scheme to smaller scale gravity radar, because grid size is getting smaller and there is always a grid scale, and this was somehow missing. So this implementation is based on the same formulation, basically. And they also have some ways to parameterize form drag and non-stationary drag. But at the same time, this is rapid refresh forecast system, which is NOAA's flagship rapidly updating convection allowing ensemble prediction system. And they use the same formulation basically. on the right, you see gravity wave physics, and you see the same references. So this Kim-Arakawa scheme and extension is currently used for both global and regional formulation, models of the National Weather Service operations. And this is one of the things that my branch does. We conduct surveys, field surveys, asking field people whether the models are meeting their needs. And we worked on RTM-IRMA, real-time mesoscale analysis, and unrestricted mesoscale analysis is kind of the most popular regional analysis system. And don't worry about this, please, and just see the yellow highlighted entries. So over complex terrain, there are phenomena that are not captured where. And here, complex terrain I define by areas with large variations of terrain. So it's not just mountains, but valleys, coastlines, islands, and lakes. And the system is struggling over that area. And we did the same for the deterministic regional system called high resolution rapid refresh model and low resolution counterpart. You can see almost the same phenomena not captured where. And part of the reason is this model provides the analysis system with initial conditions. So errors are propagating to downstream systems. And this is ensemble version of the regional forecast system called HREF, high resolution ensemble forecast system. You see almost identical things. Of course, there are other issues related to convection, winter weather, and aviation, etc. But these are really problems. Forecasts complain a lot about this. And we get the idea. So the survey says we need to better represent terrain effects, which is a major issue for National Weather Service analysis and forecast system. So based on the survey and our own analysis, we request the developers to reduce the systematic biases. And we do that by developing requirements. So my office branch doesn't work on solutions directly, but we write requirements, which are a set of guidelines for the developers to meet. So we tell them to improve it. Actually, it's quite fun telling them what to do without actually solving the problems. But my modeling background helped me do this. And we can propose solution idea, although we don't solve problems. And that is based on the Kim-Arakawa formulation. I don't have time to go into details, but that was pretty handy. So I can say a lot of ideas, but not today. And this is an example of one of the applications to observational data quality control. So here I show an area called Canaan Valley in West Virginia. And that area is well known for radiation cooling of air, COLPO, which is constantly under forecast by National Weather Service official forecast. So it eventually made it to the headline of Washington Post. So we needed to do something, and we kind of analyzed the cases. And this is the area, and it looks like a bathtub, very flat bottom, but surrounded by a rim of slopes. You can see those temperatures in Fahrenheit are pretty stable along the rim, but in the valley it's like 20 degrees colder. The problem is the observation data in the valley floor is rejected. We know this is genuine signal, but it's rejected erroneously by the quality control process. And that's because of some complex QC algorithms that take into account the nearby points. And also, the model that provides initial condition to this analysis system is not capturing the phenomenon. It's a double the trouble. And so, again, we tell them to fix it. So we need more intelligence, not just some flow dynamical oriented based algorithm that doesn't understand the physics. So we need to get some physics-based, more intelligent, maybe machine language trained algorithm to avoid this kind of situation. And again, the Kim-Arakawa scheme comes in handy. So it's very useful. And I have solution ideas that I handed to the developers. it's up to them to use it or not use it. So I don't think I need a summary slide, but I made a habit of making one. So my point is I'm indebted to Professor Arakawa and also Professor Kim, who profoundly influenced my professional career. And Professor Arakawa basically taught me how to be creative, persistent, and perseverant, which was pretty compatible with my own motto of never ever give up. So my stubbornness helps in this case, in research. The Kim-Arakawa scheme is started with weird and crazy ideas, but thanks to Professor Arakawa's encouragement, it evolved into a creative scheme. So I really appreciate his help. 30 years after the Kim-Arakawa scheme was first developed, the formulation and concept embedded in the scheme applied in various ways to National Weather Service operational weather forecasting and also warning service systems. I talked about application to data QC, but it can be applied to downscaling and also some, as I briefly mentioned, machine learning training of physical algorithms. So unofficially, on behalf of National Weather Service, I thank Professor Arakawa for his contribution. Okay, remaining few minutes, I'd just like to share some moments with Professor Arakawa. This is when I first came to UCLA. And this, I see Professor Yanai and Arakawa. And Professor Kim visited, and here's Professor Utuli and I. And my parents visited Arakawa, Professor Arakawa, and actually my father was a meteorologist for KMA, and he was director of Forecast Bureau and also Climate Bureau. Some colleagues, AMS poster, I see Mrs. and Professor Mechoso, and some birthday celebrations. And I don't remember this occasion, but I see Steve Kruger, Dave Render, and some more people. And this is taken during the AA Fest in 1998. And I had a tripod, and outside in the dark, I proposed to take this picture. Professor Arakawa here, Bob Haney, Wayne Schubert, J.W. Kim, Dave Randall, Steve Lord, Vincent Chow, Jin-Ho Moeng, Chi-San Liu, Murthy, Kruger, Jae-Ming Chen, Sajal Kar, Kwan-man, Jella Connor, Choi-Chung Lin, Martin Keller. So I think this is was a memorable moment. So that's it. Thank you.
Questions?
Sorry if I spent overtime.
No.
Can you say what the AA Fest was?
Good question. Festival? Was it festival? That's the nickname for the symposium we had here in 1998, I think. Okay, I have a question. What about non-orographic gravity waves? Especially, especially convectively generated.
Yeah, that's a good question. I wish I had the slide in front of me. So actually I came up with, just describing what I did. I came up with an idea of applying this Kim-Arakawa scheme to convective gravity drag because I found some similarity between the two different sources of gravity waves by treating that quantity that defines the heat sources to mechanically launched, thermodynamically launched waves, just like some parameter in my scheme. So I came up with an idea of having another version of scheme that covers the ocean and conductive areas. It's very important because they propagate up and become non-stationary schemes. So there are different types of schemes called spectral gravity drag schemes covering those non-stationary waves, but actually they come from the troposphere. They may have started as stationary waves and they just become, picked up some non-transiency and become non-stationary waves. So I have a scheme that unifies the three components, auroric part, convective part, and spectral part, in a very efficient way, and didn't get to publish it in a paper, but presented it at a conference. So convective graduating is very important, maybe sometimes more important than the auroric part when they launch pretty high in the atmosphere.
Yes.
Thanks for the talk. You mentioned of this briefly. I just wonder whether you can comment more as the model resolution becomes higher and higher. We are partially resolving gravity waves. So how do we move on this kind of scale-aware gravity wave parameterization?
Yeah, that's a very good point. And my schemes, I really try to make them scale aware. And they are, in spatial scale, they are scale aware, as I've shown. But in time, I mean, when we distinguish between regional scale and global scale, I call it scale aware. But when you go into like proportion to the grid sizes, it wasn't entirely scale aware. So my colleagues at NSET tried really hard. Actually, one of them includes Murthy, the picture here. Murthy and Sajal Kar work at NSET. And their team tried really hard to make it scale aware, but they had to do some tuning. So maybe my scheme is not capable of handling this scale awareness completely. But at least I have a parameter that you can kind of make it grid size dependent. Very good question, but it's very hard to do.
My question actually follow up to Lot's question. I was just curious, in general, if this scheme can handle things like how gravity wave couple with QBO, or how gravity wave handle with structural sudden warming in general, and what can we do as we have higher resolution and models, then we may need less of the gravity wave.
Yeah, that's a good question. I want to talk about something called seamless prediction capability of model. So sometimes we have different applications for short range weather, medium range, climbing, and S2S, and we're tweaking the physics differently among those applications. That's not true seamless forecasting, prediction capability. So personally, I try to stay with the same set of physics, for example, and make it good for all the applications. It should be good for the short range forecast without data assimilation, first of all. And it should be good for long-term forecast or simulation. So by doing that, I think we have a chance to make it really scale aware. Otherwise, we'll have issues popping up in all the applications. But it's very much easier said than done. So.